Good morning, students. Welcome to video lecture on microwave and optical fiber communications. Subject code U18EC709. Topic: nature of light and optical laws. Reflection and refraction of light at the boundary between two media of different refractive indices. The refracted ray will lie in the plane of incidence. Consider material 1 and material 2 separated by a boundary. When a wave is traveling from one medium to another medium, uh, it is refracted in medium 2 and reflected into the same medium. Snell's law will give the relation between the angles of incidence and refraction. Incident angle is represented by theta I and refracted angle is represented by theta R. Now here refraction is the bending of light in a particular medium due to the speed of light in that medium. When a light enters from rarer to denser, denser to rarer, you can observe how the light bends in the other medium in the next slide. Refractive index. It is represented by n, and it is a ratio between speed of light in air and speed of light in medium. The refractive index of vacuum is 1.0. Water refractive index is 1.3 and glass refractive index is 1.5. When a ray of light is incident at the interface of two media with different refractive indices, it will bend either towards or away from the normal based on the refractive indices of the medium. Snell's law. Snell's law states that how light ray reacts when it meets the interface of two media having different indices of refraction. Here you can observe the light is entering from glass to air. It is the incident angle and it is the refracted angle. Here the light is entering from glass to air means uh, it is entering from denser to rarer because the refractive index of glass is more. Here you can take theta 1 as angle of incidence, theta 2 as angle of refraction. N1 is the refractive index in medium 1, N2 is the refractive index in medium 2. And you can take the notation either in terms of theta or pi, doesn't matter. According to Snell's law, the refraction can be represented as, you are supposed to remember, En1 sine theta 1 is equal to En2 sine theta 2. N1 is the refractive index in medium 1, theta 1 is the incident angle, N2 is the refractive index in medium 2, theta 2 is the angle of refraction. Once again, I am repeating. Snell's law gives the relation between incident ray and refracted ray only. A sample example problem. Just go through. When a light is entering from rarer to denser, based on Snell's law, um, it bends towards the normal. Here it is the position of boundary and it is the position of normal to the boundary. When a light is entering from rarer medium to the denser medium, it bends towards the normal. You can observe here theta 1 is the incident angle, theta 2 is the refracted angle. Once again I am repeating, When the light travels from rarer to denser medium, refracted ray will bend towards the normal. Let us move to another problem. Here, when a light enters from denser medium to rarer medium, it bends away from the normal. You can observe with the help of the given model problem. Once again, here we applied Snell's law. N1 sine theta I is equal to N2 sine theta R. Theta 1 is the instant angle. Theta 2 is the angle of refraction. You can observe when the light is entering from denser medium to rarer medium, it bends away from the normal. Just go through the problem. Total internal reflection. Before going to the total internal reflection, you just make a note of how the light refraction of light takes place when it is traveling from denser medium to rarer medium. Here in first diagram, you can observe theta 1 is the instant angle, theta 2 is the angle of refraction. When the angle of instant is less than critical angle, uh, the light ray will refracted into medium 2, and when the angle of instance is equal to critical angle, the angle of refraction is 90 degrees. That is angle of reflect, the angle at which the angle of refraction is 90 degrees at a position where this particular theta 1 angle is called critical angle. And when the instant angle is beyond increased beyond the critical angle, the ray will be reflected into the same medium, and this concept is called total internal reflection. Here total internal reflection occurs when the angle of instance is greater than a certain angle, that is called critical angle. And the total internal reflection is a phenomenon in which a ray of light traveling from a denser medium to a rarer medium is reflected in the denser medium at the interface between the two media. Here you can observe how the signal propagation takes place with the help of total internal reflection. It is cladding and core. With the help of total internal reflection, you can observe the light propagation in optical fiber core. The very important point is the total internal reflection allows light to be remain inside the core. Uh, Here you can observe how the total internal reflection takes place when the angle of instance is uh, above the critical angle. If it is below the critical angle, the ray will escape from the core, sorry, from the cladding area. And when the angle of instance is exactly equal to the critical angle, it just grazes the surface of the core cladding area. And when the angle of instance is greater than critical angle, total internal reflection takes place. Now, according to Snell's law, you can determine the critical angle, that is the angle of instance at which the angle of refraction is 90 degrees, that is called critical angle. Now here, by making theta 2 is equal to 90 degrees, you can determine the angle of instance The angle of instance theta I or theta 1 is equal to theta c when it is sine inverse n2 by n1. This can be determined based on Snell's law. Meridional rays and skew rays. A ray that passes through the axis of the optical fiber is called meridional ray, and a ray that travel through the optical fiber without passing through the axis. It may take helical path. Thank you. We will meet with the next lecture.